In today's lecture, we're going to look at the development of the periodic table and some basic information that is contained within the periodic table. Now, the periodic table, as most of you have already figured out, is a very useful tool for chemists. There's a lot of information, and we've just touched on the information that is available in the periodic table. That's why you usually find a periodic table on the wall in every chemistry room in the country and around the world. It hasn't always been around, though. So let's take a quick look at how it developed. The first individual that really tried to classify the elements was Dobereiner, early 1800s. He came up with what was known as a triad system. And what he did was, again, at that time, remember that many of the elements we see on today's periodic table were not known, just the top part of the periodic table. So what he did was he found that there were groups, and for him it was groups of three he found that seemed similar. And examples were lithium, sodium, potassium. That was one of his triads. Another one was chlorine, bromine, iodine. And if you look at those elements on the periodic table, they're all in the same column. Columns are what we call groups or families because they share some common traits, like lithium, sodium, potassium. They're all soft gray metals, react with water, react with oxygen in the air. So, they do all have similar characteristics. Same way, when you look at group 7A, all highly reactive nonmetals for chlorine, bromine, iodine, poisonous. So he was onto something. Then Newlands, about 1865, he had the octave system. Now, Newlands actually saw that every eighth element seemed to have similar properties. Once again, he was seeing the idea of the groups or families. Because if you look at the top of the periodic table, let's take a quick look at that. If you look at, say, numbers there, actually beryllium is 4, magnesium is 12, 8 down. And then magnesium is 12, calcium is 20, another 8 down. So every eighth element seemed to have similar properties. And at the top of the table, every eighth element ends up being in the same column. So he's actually seeing what we know, again, as groups or families. Same way if you go over here, the top two, oxygen is 8. Then you have sulfur, 16. Lithium is 3. Sodium is 11. Potassium is 19, every eighth. So once again, he was on to something. His biggest problem was that he actually put an unfortunate name. When he said octave, most of the scientists thought about music, and they figured music and science were not related, so no one paid much attention. The big name in the periodic table, though, is Mendeleev. Mendeleev, in about the same time, developed the first true periodic table. His looked very much like the periodic table that we find on the walls of chemistry rooms across the nation. He arranged his elements in order of increasing atomic mass. He believed that the atomic mass determined the properties of the element. He made it so that those elements with similar properties ended up in the same column, and he called them groups or families. He was able to predict properties of elements that were not yet discovered. And that was the thing that really sold people. When he first came out with the periodic table, no one paid much attention to it. But then what he did was he left blanks for elements that he figured we had not yet discovered and would be discovered. And he not only left blanks, he made some predictions about it. The famous one is germanium. It was not discovered yet, but he left a place in his periodic table for germanium 32 right under silicon, and he predicted that he predicted its density, predicted its color, he predicted its melting point, and he came very close in all three. So when he was able to do that, actually did it 3 times. By the time the third element came about that he had predicted, people paid attention to it, and his periodic tables accepted, and he became famous, and again, today we call Mendeleev the father of the periodic table. The big change, though, in the periodic table really was Moseley in the early 1900s. He did some experiments, and he found that the atomic mass did not determine the properties of an element, because you have isotopes that have different masses, same element. He figured that, or found in his experimentation, it was actually the atomic number, which is the number of protons. So he figured the number of protons, that's what determined the properties of an element. So actually the periodic table was based on atomic mass until Moseley. After Moseley, it's atomic number. Now, it so happens as you get more protons, you usually get more mass, but not always. It did correct one big problem that Mendeleev saw. The iodine and beryllium actually were switched on Mendeleev's table. And he knew that wasn't right. He knew iodine should be with fluorine, chlorine, bromine, and iodine, but yet it didn't fit due to based on mass. But what he decided was that we really didn't do a very good job of measuring the mass, and eventually that would be found faulty and it would fall into place. Well, never did, but Moseley explained why. It's atomic number that we should be organizing the elements by. And when you do that, all the elements fall into their nice columns and they fit with the elements above and below them. So that was the last big change really in the periodic table. Now let's take a quick look at the difference between metals and nonmetals. Once again, we can take a look at the periodic table. If we take a look at the periodic table, the metals and nonmetals, actually there is a dividing line that's shown up on some periodic tables. It starts underneath boron. It's kind of like a stair step down through the periodic table. Everything to the right of that stair step is considered a nonmetal. Everything to the left of it is considered to be a metal. What's the difference? Well, general characteristics, metals have luster. In other words, they're shiny. Metals are malleable. They can be pounded into a sheet. Metals are ductile. They can be drawn into a wire. And metals also conduct heat and electricity. Another thing that we see here, if you look, those elements that are right on that stair step here, like silicon, we'll be working on that in an upcoming lab. Some of these, because they have characteristics of both metals and nonmetals, are called metalloids. Silicon's a good example. When we use it in lab, you will see that it is brittle, can't pound into a sheet or draw it to a wire. It doesn't conduct heat and electricity well. That's why we can use it in insulation, silicon caulk. But it is shiny. It does have luster, which is a metal characteristic, even though it's on the non-metal side. So it is actually a metalloid. So all those things that touch that stair step can show properties of the metal or non-metal, so we call them metalloids. The other thing then, wanted to make sure we understand, is that the columns up and down, remember, those are known as groups or families, and some of them, the characteristics are very close. We actually give them family names. For instance, group 1A, those are the alkali metals. Group 2A are the alkaline earth metals. Then as we come over here, group 7A, they have a name, those are the halogens. And then group 8A, none of those react, so those are known as the noble gases. Other terminology, we have the rows across the periodic table. Those are known as periods. So any row across the periodic table, those are periods. So if you hear that terminology, that is a period. So this is just a quick look at how the periodic table developed and a few characteristics that you can pick out. Now, something we will be working on is electron configuration, and that we can use the periodic table to figure that out. And really, electron configuration just tells where we expect to find some of the different electrons that make up an atom. So we will be using the periodic table to get us electron configuration, and we'll also be using it for the size of atoms and how hard it is to tear away electrons from atoms. All that information is actually locked up in it, and we'll see how to get the key and get it for ourselves.